Hello everyone, in this video I'm going to be talking about how you're going to be calculating the theoretical yield of an ester when you're doing a Fischer esterification, which is technically the combination of an acid with an alcohol in the presence of a strong acid, something like sulfuric acid. That's usually in a catalyst, so maybe 2 to 3 drops of sulfuric acid is going to be good enough. So when you do make the product at the end of the day, which is going to be an ester and water here, it usually sets up an equilibrium, and even if it doesn't set up an equilibrium, it's the reaction is fairly product favored. So I want to go ahead and draw an arrow that's actually going to be much smaller onto the reverse side. So your product is actually going to be, one of them is going to be water. So we're going to have the water coming from this OH here and this hydrogen here. So that makes the water. So I'm just going to go ahead and write that down here. That's going to be your liquid, obviously, and you're going to have your remaining product that's going to be the ester. So you're getting that part from the acid, and you're going to be getting this part from your alcohol. So we're going to have an oxygen there. I'm just going to go ahead and draw that out. So it makes this particular one makes an ethyl acetate, and our job is to figure out how much of that ethyl acetate is going to be made theoretically, and obviously how much you actually make in the lab, and eventually you're going to have to figure out the percent yield. And this does not really go into completion as it sets up an equilibrium. That's why it's important to use the equilibrium constant to figure out how much theoretically you're supposed to make here. And typically, you will be given a data set where you're going to be having the densities, the molar masses, or whatnot. Most likely densities, because molar masses, you can certainly calculate those out. And also, I do want to mention that you may not be necessarily only dealing with this acetic acid or just this ethanol. I just have those as an example, but you may very well be using the different alcohols or maybe multiple alcohols in a classroom where where different groups are trying to figure out how much of ester you're going to be making at the end of the day. So I do have two reactants and I do have two products. And now keep in mind, water, even though you make this is in a liquid form, and a lot of time, and mostly you have learned in Gen Chem that you don't include the liquids and solids in your um, equilibrium constant expressions. Well, that's not always true. That's water, even though it's a liquid, it's actually a part of the reaction. It's one of the products that's made during the process, so you must include that in the equilibrium constant expression. So you could have a very well different settings where you maybe you're told you're using this many milliliters of your acid in your alcohol, or maybe using these many moles for acid and your alcohols. And then you're going to have to figure out how many milliliters you need in that particular case. So either way, these both are going to be liquid, so very likely you're going to be measuring those either in milliliters or in grams, most likely in milliliters. So if you do measure those out in milliliters, you're going to have to eventually figure out their masses and then eventually their moles. All right, and then we can worry about the molarities a little bit, but dealing the equilibrium constant here in moles or in molarities is going to be the same thing. So let's suppose I have maybe 5 milliliters of this acid being used. So I'm going to go ahead and write down 5 milliliters here. And I have, let's say, your alcohol, since it's going to be relatively expensive than the acid, it's most likely going to be your limiting reactant. And I'm going to go ahead and say this is probably going to be maybe, let's say, 3 milliliters. All right, I'm just making up numbers here so that we can use those in the calculations, and you may very well have different numbers. So that's going to be 3 milliliters right there. And using the densities, I want to figure out what their mass is going to be so that eventually I can figure out their moles. So let's start out with your acid first. So we are using 5 milliliters. So in that 5 milliliters, I can use the density of acid that's going to be 1.049 grams per liters. So that way your milliliters cancels that, and then you got to just multiply that by 5. So that's going to be 5.25 grams. All right, I'm just going to keep 2 decimal places for right now. And then I can do something similar. I would have 3 milliliters and 3 milliliters of alcohol. The density of alcohol is 0.789 grams per milliliters. So we have 3 times 0.789. That's 2.37 grams. So I'm going to go ahead and put that out there. Okay, and then eventually I also want to figure out the moles for each one of them. And to figure out the moles for, suppose, the acid, I would have 5.25 grams of your acid here. And certainly I want to use the molar mass to find this moles here. So I would have 1 mole of your acid. In this particular case, it's going to be 60.1 grams of your acid. That's going to be 5.25 divided by 60.1. So it's going to be 0.0874. Okay, so I'll just go and write that down here. 0.0874 moles for that. And I'll have something similar for the alcohol as well. So we're using 2.37 grams of your alcohol. And then I want to go ahead and use this smaller mass, which is going to be 1 mole of your alcohol. And that's going to be divided by 46.1 grams of your alcohol. And so that way your grams cancels out, in the previous grams cancels out as well. Make sure your units cancels out. Only the units you're looking for, that remains. So this is going to be 2.37 divided by 46.1. That's going to be 0.0514. Okay, so I can just go ahead and write those down. 0.0514. So you can clearly see this is a 1-to-1 mole ratio on all those. And I'll rewrite that in the generic form. And then eventually, the moles of acids are much more than the moles of your alcohol. So your moles of alcohol is going to be the limiting reactant in this particular case. So you can kind of, you know, like how I'm going to be looking at in terms of the theoretical yield. So that's what we really have as of now. Obviously, your water and ester are going to be the products. We don't know much of the information on those yet. That's what we're really trying to figure out. So I think I'm ready to write down the equilibrium constant expression now. And before I do that, maybe I can go ahead and write in a generic reaction where I say I got this acid and I got this alcohol. So maybe I can just write down ROH, and it sets up an equilibrium with an ester, and then we're going to have water being made. So I can go ahead and make an ice table here, and I'm going to go ahead and write those down in terms of moles. You don't necessarily have to write those down in terms of molarities, and I'll tell you why in a minute. So let me go ahead and write those down in terms of moles. So I have the moles of acid is 0.0874 here. So initially I got 0.0874 moles of acid. The moles of your alcohol is 0.0514. So it's 0.0514. Initially, you don't have any esters made. So I'm going to take an assumption that if I lose X amount of acid, I'll lose X amount of your alcohol. And in the process, I will be making an X amount of what of your product. So at equilibrium, I should have 0.0874 minus X for your acid, 0.0514 minus X for your alcohol, and your X for the ester and your X for your water here. So when I'm writing my equilibrium constant here, so your KEQ is going to be obviously the concentration of your ester, concentration of water, divide that by the concentration of your acid, and the concentration of your alcohol. So remember, your alcohols, your acids may very well be different depending on what particular acid and alcohol you're using in the process, but how you're going to be calculating it would stay the same. So KEQ will have different numbers based on what particular acid and alcohol you're using. It usually runs anywhere between 3 to 5. So I'm gonna assume that your KEQ for this particular one is, let's suppose, 3.9. All right, so that's the number we're gonna be using here. Now, the concentration of acid is obviously going to be the moles of acid divided by the total volume, all right? That's how we really find the concentrations. Remember, all these terms that I had in the product or at the equilibrium, I have written those down as in terms of moles. I have not written any one of those down in terms of the concentrations. If I have to write those down in terms of concentration, the only thing I really need to do is divide all those by the total volume that we are using in the solution. So what's really going to be your total volume? So I'm just going to go ahead and, just say here, divided by the total volume, and even here, and even here. So that will eventually give you the concentration. But if I have to go back and really worry about what's going to be the total volume, I can go back and be like, okay, I'm using 5 milliliters of your acid and 3 milliliters of your alcohol. And assuming they're additive, it's going to be about 8 milliliters. Now, also remember you're using this catalytic acid here, but that's you're only using 2-3 drops. So that's really not going to make any significant difference in their volume. Now remember that volume is going to be the same for all of those. So that's really not going to be any factor in there in whether you use the moles or whether you use the molarities. Because when I go back here and rewrite the KEQ here, so I would have, let's say, 3.9. So I'm just writing down the KEQ. Your ester is going to be X over V. That's, remember, your volume. And your water is also going to be X over volume. And then the concentration of your acid is going to be 0.0874 minus X, and we're going to be dividing that by volume as well, and then 0.0514 minus X, divide that by volume as well. So since you have the same number of reactants in product, and you have the two volumes in the denominator, two volumes in the numerator, they would eventually cancel out. So that's why I said, you don't really have to worry about taking the volume into consideration here because they would eventually cancel out. So we could just worry about the moles only here. So, all right, so this eventually gonna be simplified into, let's go ahead and write that down as 3.9 equals to X times X, and then in the denominator we would have 0.0874 minus X and 0.0514 minus X. So if I could somehow figure out what that X is, we will be able to figure out the amount of moles being made for this ester and this water here. Okay, so that's what we really need to do. And let's just try to solve this out. I'm just going to go ahead and copy this down here. If I duplicate it there, this becomes x squared. Now this is going to become in a quadratic, and it's not going to be great to ignore these x's like you would have ignored previously when you take Gen Chem 2. So once this becomes in a quadratic, you would have to actually use a quadratic formula here. So this is going to be x squared. I'm going to use a FOIL here so that this gets multiplied here. Let me change the color maybe. So this gets multiplied here, and then this gets multiplied here, and then you're going to have this getting multiplied here, and this getting multiplied here. And then we'll want to see what we really get out of it. So first of all, I'll do the one that's in the denominator uh, with the green one. So I have 0.0874 times 0.0514. So that gives you 0.0045. Okay, I'll keep 4 decimal places for right now. And then I will have minus 0.0874x. And then I'll do the top ones now. So it's going to be minus 0.0514x. And then plus x squared. Okay, so that's what we got. I'm just going to copy everything down so we still have 3.9 here. X squared still on the top. To make this a little bit more simple, we're going to be adding these two terms together because they are the same terms. And then that will give me, so that would still be 0.0045, and that would be 0.0874 plus 0.0514. So it's going to be 0.1388x plus x squared. So now I can multiply both sides by this number. All right, so when I multiply this both sides by this number, I'm going to be multiplying this by 3.9 here. So I would have 3.9, and then I'm just going to be multiplying this whole thing by that number, and that's going to be equal to x squared. So let's see what we get here. So it's 3.9 times 0.0045. So that's going to be 0.0151755, and then minus, I have 3.9 times 0.1388. That's going to be 0.54132x, and then I'm going to have plus 3.9x squared, and that's going to be equal to x squared already. I can subtract both sides by x squared. So when I do so, I'll get this right here, but not 3.9, but rather now 2.9, and that's going to be equal to 0. So this becomes in a quadratic, and if I want to go and rearrange it, I'll write it this way. So I have 2.9x squared minus 0.54132x, and then plus 0.01755, and that's going to be equal to 0. So in the quadratic here, this is going to be your A, this right here is going to be B, and this right there is going to be C. When you use the quadratic formula, it's going to be minus B plus minus B squared minus 4AC divided by 2A. All right, so that's the quadratic formula that you want to be using here. So let's just go ahead and plug these numbers in. So we have x, your b is going to be minus 5.54132, so minus 0.54132 plus minus, okay, so I'm going to go ahead and write that down, minus 0.54132 square minus 4 times your A is 2.9 and your C is 0.01755. And all that is going to be divided by 2A, which is going to be 2 times 2.9. All right, let's just try to solve that out. When this minus multiplies with that, that's going to become plus, so that's just going to be 0.54132 plus minus. Let's see what we really get inside. So I'm going to just get everything 0.54132 square, and then you got minus, and then these are being multiplied 4 times 2.9 times 0.01755. So whatever you get, you got to take the square root of that. So when you take the square root, this comes out to be 0.2991, and in the division, you're going to have 2 times 2.9, so that's going to be 5.8. So what I'm really going to do here, since we have plus minus together, one time we're going to take that as a plus, and that would be your x1 value, and one time we're going to take that as minus, and that would have been your x2 value. Because it's in a quadratic, you're supposed to have two values for the x. So let's say one time, we'll take that as plus. So that would be plus here. And for the second time, To find the second value, we're going to take that as a negative here. Okay, so let's go and solve for x1 and x2 here. Your x1 is going to be 0.54132 plus 0.2991 and divide that by 5.8. So it's going to be 0.1449, and your x2 here is going to be 0.54132 minus 0.2991 and divide that by 5.8. So it's 0.0417. So now, if we go back, now we got these two values for the x, and I can probably copy both of these. Maybe copy both of these down, and I want to go back and compare. And just cut them. Okay, I'm going to go back and compare with what I really have on the top there. So two values I'm getting so far for the x are this right there and this right there. Those two values, and then I really got to worry about which one is really a valid value. Now you can clearly see what our starting materials are. We're actually starting out with 0.08, 0.05. So I can't really make anything more than that because these X are actually representing the moles here. So if you're starting out with these small values, I cannot really make more than what we are really starting out with. This quadratic value right there is going to be invalid. It's going to be invalid in terms of what values we got there. So this is the one. The second one is the valid value here. That's the one that we really want to go ahead and take. So your X here for the ester and for the water comes out to be these many moles here. So we're going to have, just go ahead and write that down. For the ester, it's supposed to be 0.0417 moles. And even for the water, we're supposed to have 0.0417 moles. And I could care less how much we are really, leaving the acid and the alcohol. You can certainly calculate that by plugging the value of X here. But what we're really trying to figure out is how much ester you eventually get to make. So since now I know this is how much ester I have made in terms of mold, I can go back and figure out the mass of the ester and eventually the volume of the ester. So now I'm working it backward. Okay, so let me go ahead and do the back calculations to figure out to the volume of the ester that you're radically supposed to make, and we are, let's say, going to be starting with 0.0417 moles of ester, and then in the first step, I want to go ahead and find the moles, grams of ester. So now I have 88.1 grams of ester per mole. That's a molar mass. And then once I know the moles of grams of ester, I can go ahead and figure out, well, maybe I can go ahead and figure out the grams of ester first so that I can fill in the table. So how much that gonna be? Let's see. We have 0.0417 times 88.1. That's going to be 3.67 grams of ester. And now I want to go ahead, let's go back here and plug that in. So that's 3.67 grams here. And I can go ahead and fill out the volume of ester. So that's how much ester we theoretically supposed to make. And the volume of ester here is going to be 0.902 grams per milliliter. We're going to use the density here. So we want to divide that by 0.902. So that comes out to be 4.07 milliliters. So roughly we're supposed to make 4 milliliters of ester here as our theoretical yield. So this is how you're really going to be calculating the theoretical yield of ester and Fischer esterification. And certainly you can calculate the, the theoretical yield or the mass of the water, but, I can leave that for you guys. And then if the question does ask you like how much alcohol and how much acid you have left at the end of the day, then you can go back in there, plug those value, the X values here, and then that will tell you how many moles of acid and how many moles of alcohol you have left, and you can work it backward. But you're obviously the main concern is how much ester you're supposed to make. Now, let's say you do the lab and everything, and your actual ester that you retrieve might be like 3.5 milliliters. So let's say actual volume of the ester after you distilling it and everything is 3.5 milliliters. Then your theoretical volume is supposed to be 4.07 milliliters. So that means I can find the percent yield for this particular one as 3.5 milliliters divided by 4.07 milliliters times 100. Now, you can very well calculate this percent yield from the grams of ester that you're supposed to retrieve and actually got. It will still give you the same number, so it doesn't really matter. So 3.5 divided by 4.07, that's going to give you about 86 roughly as your percent yield in this particular case.